Hello students, so in the previous class we already discussed the one chapter that is related to electrolytic cell where electrical energy is converted into chemical energy. So there you require an external electrical source, so we generally use a battery to provide electricity, and by providing electricity we are now carry out some chemical reaction, and you will see some different substances are forming at their respective electrode. That what you observe in a electrolytic cell. So in this new chapter we are discussing the other category of cells that we will call galvanic cell, where chemical energy is converted into electrical energy. So here you can see because of the spontaneous chemical reaction that's taking place in the electrodes, you can see electrical energy is producing. So in some of the normal cells that we already know, that is based on the galvanic cell. So if you're getting an electrical energy from a cell, which means that is a galvanic cell, or otherwise we will call voltaic cell. Galvanic cell, or another name is voltaic cell, or simply we will call electrochemical cell. Electrochemical cell. So why they are called electrochemical cell or galvanic cell? Here you can see chemical energy is converted into electrical energy. So a chemical reaction will be taking place in the electrodes, and you can see electrical energy is producing. So let us understand this. What's the setup of this galvanic cell using our conventional galvanic cell that we will call Daniel cell. So here you can see two half cells will be there. For example, I just take two the cells where a zinc metal is connected. A zinc rod is dipped in zinc sulfate solution, its own solution, ZnSO4, zinc sulfate solution, and another electrode on the other side where I have taken copper electrode. Copper electrode is dipped in its own solution, that is copper sulfate solution. So two electrodes are taken, one in which a zinc rod is dipped in zinc sulfate solution and copper rod is dipped in copper sulfate solution. So now what we are doing, we just we connecting these two half cells. This is we can consider as one of the half cell, and this another half cell. So two half cell combines to get a complete cell. So here we are connecting these two half cells by through a metallic wire. A metallic wire will be connected, and a meter is there in between the two half cells, and this is metallic wire. A metallic wire will be there. So metallic wire externally connecting the two electrodes. One a zinc rod which is dipped in zinc sulfate solution, and copper rod dipped in copper sulfate solution. Now to connect internally two half cells are connected by another a glass, a U-tube, a U-shaped vessel that we will call salt bridge. This we will call salt bridge, where salt bridge internally connecting the two solution, and you can see a particular solution, a KCl solution is filled here. KCl in agar agar, that's one of the jelly like substance that we used in the inside this U-tube, that we will call salt bridge, where now a KCl or KNO3 such solutions are filled in a substance that we call agar agar. It's not something a jelly substance obtained from mainly from red algae, like that. So this is now inside there will be KCl solution will be there, and what's the function of salt bridge? Just very important. Understand, this salt bridge connect internally these two solution, and also this salt bridge makes sure that no there is no excess of charge developed in the each half cells. Doesn't allow to accumulate a particular ions in each half cells, which makes sure that no we can understand what's the natural tendency of these two electrode, because if same electrode is taken, for example here zinc in zinc sulfate, zinc in zinc sulfate, doesn't make any difference, because no there are no real potential difference is developing between the two electrodes. So here actually by using this particular cell we can understand what is the natural tendency of zinc with respect to copper. Now here it is observing that zinc having more tendency to undergo oxidation compared to copper, or if you compare these two, copper having high tendency to undergo reduction compared to zinc. So a different tendency will be there. Zinc undergo oxidation, copper undergo reduction, which means oxidation means release of electron. So as a result of oxidation, zinc now releases electron that going through the external metallic wire, and here you can see copper 2 plus ion will be there in the solution from the copper sulfate solution, that gains electron to deposit copper in the copper electrode. So now a different tendency you can observe when these two half cells are connected each other. So let us now understand what's happening here. Here, this we can call as anode. Generally, anode will be on the left side and cathode will be at the right side. Where now zinc, don't confuse the holes. Vessel is anode. This is anode. Zinc rod is actually anode, and the copper rod is acting as cathode. Remember, whether it's an electrolytic cell or galvanic cell, always oxidation takes place at the anode. So let us discuss what is anode here. It is zinc, and zinc converted into Zn2 plus ion plus 2 electrons. Zinc is a metal in the aqueous form, you can see. So this is we call oxidation. Two way you can understand this is oxidation, where zinc is converted into Zn2 plus ion. So increase in oxidation number from 0 to plus 2. So that's an oxidation. The release of electron is oxidation. So both sense you can understand oxidation. With respect to a zinc rod, it is observed that copper having a tendency to undergo reduction. So copper 2 plus 2 electron gives copper, where now you can see copper start accumulating on the copper electrode. Excessive copper start accumulates. That is reduction. So copper 2 plus ion in the aqueous form gains electron to deposit as copper. So two different kinds of reaction take place. One, you can see zinc from the zinc rod, zinc is dissolving as Zn2 plus ion. So you can see the zinc disappears as the reaction proceeds, while you can see copper concentration increases, because initially let's see one a particular concentration of copper was there. Now as a result of this, by connecting this cell, you can see a copper electrode. The concentration of copper is getting increased, because the copper 2 plus ion from the solution start depositing as copper. So that's two reaction that takes place at the two electrode. So basically in a galvanic cell, it consists of two electrodes and two half cells, in which a particular electrode is dipped in its own solution, and these two have different oxidation or reduction tendency. Now why this is working as a cell? Because compared to zinc and copper, zinc have more tendency to undergo oxidation, copper have more tendency to undergo reduction. So that different tendency actually is a driving force to produce electrical energy, because from the zinc electron is released, that how much electron is released, that going through the metallic wire and gained by this other cathode. So cathode gains electron, zinc loses electron. So you can see a flow of electron takes place. Once flow of electron is there, that is electricity for you. So conventionally we are considering as the flow of electron from zinc to copper here, which means electron are flowing in this direction. which means electric current we consider in the opposite direction. So we can say electric current is flowing from copper rod to zinc rod. So this is what now a conventional galvanic cell is all about. This particular cell we can call it as Daniel cell. So when a particular electrode is dipped in its own solution, it has a natural tendency either to lose or gain electron. That tendency we can say electrode potential, and that electrode potential will vary from one electrode to other. For example, comparing zinc and copper, zinc having a higher tendency to undergo oxidation compared to copper. So that difference actually we used for the electricity to produce. So when a particular metal dipped in its own solution, you can see an electron will be released, and with respect to the solution and the metal electrode, there is a potential difference will develop. Similarly in other aspects based on their natural tendency. So we can either consider a particular electrode in terms of their oxidation tendency, or you can consider their tendency as reduction tendency. So you cannot take both, which means we have to fix one particular tendency. That's why now we consider reduction potential as the standard electrode potential, where we have that reduction potential value of a particular electrode, and we are comparing the reduction potential of different electrode. For example, here copper, it is we will discuss that how to measure copper having higher reduction potential value and a zinc having lower reduction potential value, which means the electrode which having higher reduction potential value undergo reduction, and the electrode which having lower reduction potential value that undergo oxidation. So that's the way we can consider we can compare the electrode potential of different electrode. We conventionally taking reduction tendency as their standard tendency, where we comparing the reduction tendency of different electrode. One particular electrode having high tendency to undergo reduction, which means you have to automatically understand that they have lower tendency to undergo oxidation. So they are opposite to each other. So zinc having more oxidation potential, which means definitely it having less reduction potential. So that's the way you have to understand in a galvanic cell. And another important point here, you can see always oxidation takes place, so electrons are releasing, right? So you can see a negatively charge is developing around the electrode. That why a anode is always negative in a galvanic cell, just the opposite in a electrolytic cell. So here because there is no external battery or something we are using, so we cannot say this is a positive or negative with respect to an external battery source. Here we considering anode as negative because the electrons are releasing, so you can see a negative charge developing at the electrodes. Similarly, now here you can see the positively charged ions will be around this cathode electrode, where it have a natural tendency to gain electrons. So here a positive charge will be there around the electrode, hence cathode will be always positive in a galvanic cell. That's the main difference in an electrolytic and a galvanic cell, where in a galvanic cell anode is negative, cathode is positive, just the opposite in a electrolytic cell. So that is the primary idea that you can have related to the galvanic cell. Okay, now let us discuss. This is oxidation reaction, this is a reduction reaction. Now you can combine these two, because how many electrons are released as a result of oxidation, that much electron will be gained in the reduction. So overall reaction you can represent Z plus Cu2 plus gives, just add these two and you will get Zn2 plus Cu, where zinc is a solid, copper 2 plus is in the aqueous form, Zn2 plus in the aqueous form, copper in the solid form. So here you can see a overall reaction you can represent like this, where zinc is converted into Zn2 plus, copper 2 plus is converted into copper. That's what basically at the end the reaction is taking place. So that we can say an overall reaction or cell reaction. Another important point that you can remember, how to represent the cell. How we can represent a particular galvanic cell. From the representation of galvanic cell, student has to understand what this cell is all about. Here let me represent zinc, then a vertical line, Zn2 plus, then a double vertical line, then copper 2 plus, a vertical line, and a Cu. Zinc in the solid form, Zn2 plus aqueous, copper 2 plus aqueous, copper solid. So here, a single vertical line represent the electrode and electrolyte solution, and double vertical line represent a salt bridge, which internally connect the two solutions. So that's how you can represent a cell. From this, student has to understand zinc undergo oxidation to give Zn2 plus, copper 2 plus undergo reduction to give copper. So that's the way you can understand a galvanic cell. Now, having written zinc is anode, zinc undergo oxidation, copper undergo reduction, means always zinc will be an anode or always zinc undergo oxidation. That's the way student should not think, because let me represent another cell. For example, magnesium, Mg2 plus ion, Zn2 plus ion, Zn. Magnesium solid, Mg2 plus ion in the aqueous form, and Zn2 plus in the aqueous form, zinc in the solid form. So look at here. Generally on the left hand side it will be anode, right hand side it will be cathode. Look at this particular cell, because you can construct any type of cell. So here magnesium is acting as anode, where zinc is acting as cathode, which means oxidation occur at the anode and reduction occur at cathode. So with respect to magnesium, zinc have less tendency to undergo oxidation. Hence, zinc undergo reduction and magnesium undergo oxidation when these two half cells are connected. So that's the way student has to understand. This is depending on the relative tendency of a particular electron with respect to other. So we saw zinc have a tendency to undergo oxidation when is connected with the copper. But when magnesium electrode is connected with the zinc, you can see the tendency just the opposite, where magnesium undergo oxidation and zinc undergo reduction, which obviously suggests that the standard reduction potential value of magnesium will be less, standard reduction potential value of zinc will be higher compared to magnesium. So that's the way we can compare. We will discuss the reduction potential value of different electrodes that we will discuss in the next part, where you can understand exactly which electrode will undergo oxidation, which electrode will undergo reduction, that you can easily understand. So let us discuss the let us discuss one more electrode, because it doesn't matter always you have to use a solid electrode. You have to use, here one example you can see, hydrogen is using as one of the electrode, and copper 2 plus is the other electrode. So look at this. This is also working as a cell, where hydrogen is our anode and copper will be our cathode. So hydrogen is a gas. How it works? That why we using an inert electrode. Platinum inert electrode is used, where hydrogen gas is bubbled. There you can see with respect to copper, hydrogen undergo oxidation. So it will be like H plus plus, one electron gives H. Since hydrogen monoatomic is unstable, 2H plus plus 2 electron gives H2 gas. So oxidation takes place at this anode, and reduction takes place at cathode, where copper 2 plus will be converted into copper. So it doesn't matter whether it's a solid, liquid or gas, still you can work as a cell. Now let us now discuss the functions of salt bridge generally asked in the question paper. So first point I told, salt bridge actually completes the cell. Without salt bridge generally it do not work. So a salt bridge is required which internally connecting the two solution and which completes the electrical circuit. Second point, it prevents the accumulation of a particular charge in the respective electron. So it doesn't allow a particular charge to develop, which means no KCl solution, K plus and Cl minus ions are there inside the salt bridge. So these two ions actually having similar ionic mobility. That's one of the key thing that we observe to select as a salt bridge inside the solution, inside the salt bridge. K plus and Cl minus will be there, and now these K plus and Cl minus have almost similar ionic mobility. So K plus ion and Cl minus ion, which makes sure doesn't charge is developing, excess charge is developing at the electrode. So if negative charge is more, a positive ion will come and neutralize it. Similarly, now both electrodes where doesn't allow a particular ions to accumulate more, or the ions can move through the salt bridge as well, which makes sure ionic balance is there, doesn't allow a particular charge to accumulate. So that's another function where it prevents accumulation of charges in the two electrolyte solution, where the cells by the free movement of ions through the electrolyte, or electrolyte can move through the salt bridge, or the other case as well, salt ions can move to the ions can move to the electrolyte as well. Thus it makes sure two ions are not intermixing. Two ions never intermix, but the salt bridge internally connect means these ions can move through here, and it can come to here as well to neutralize the excess charge. So that will be there. So that is a third function we talking about. Electrical neutrality is maintained at the two half cells where ionic balance is there. Next, it avoids liquid junction potential. That's now another important function where now we will discuss about liquid junction potential in the later part, where now it means when two different electrolytes are connected each other, when they are in contact each other, one having higher concentration, one having lower concentration, it is observed that the ions are moving from higher concentration to lower concentration. So with respect to that movement in that junction where two solutions are separated, there you will see a potential difference will develop. Because of that potential difference, there is excess charge will be there, which normally we don't expect higher charge will develop due to that liquid junction potential. So it will make incorrection. So for that this algorithm will actually working to avoid that a liquid junction potential to develop. As I said, it doesn't allow excess of charge to develop in the two electrolytes. So that very important. So our salt bridge actually functioning to prevent the liquid junction potential to develop. More you will understand in the later part what is liquid junction potential is all about. So that part our first part were still nowadays without salt bridge it's also working where a porous diaphragm is using where we can think like this, a thin membrane in between a thin membrane will be is connecting in between the two electrodes, where this works like a salt bridge, where doesn't allow a particular charge to develop in the two electrolytes, which will make sure that cell works nicely. So that we will call cell diaphragm, porous diaphragm, okay. which will now work like salt bridge, doesn't allow a particular charge to develop, allow the natural tendency of the two electrode. If anode have a natural tendency to undergo oxidation, cathode have a natural tendency to undergo reduction. So allows, by allowing the natural tendency, this no porous diaphragm actually working just like a salt bridge. So that's all about the normal, that's all about the starting related to the our galvanic cell, or also called voltaic cell, or another name is electrochemical cell. So in the next class we can discuss more. So thanks for listening. Let us wind up.